Okay? And if we were going to set it all up to solve for our equilibrium expression, okay, our KEQ equals our N2O4 over our NO2, remember, squared. Okay? And then it asks this question, if we have 2 molar NO2 and 0.5 molar N2O4, are we at equilibrium? So what we went through and did is said, okay, well, if we're going to solve for this to see if we're at equilibrium, we would say equals, and then we'd go through and plug in those numbers. We had 0.5 molar for our N2O4. We had 2 molar for the NO2 squared. We had 0.5 divided by 4, which gave us 0.125, right? Okay. So we ran all those calculations. Okay. Sometimes my color coding is on point. This is an issue or a time in space that the color coding is on point. Is that a true equality? Okay. We know the KEQ is equal to, yes, all that stuff, but we also know the KEQ from the given information is 217.4. Is 217.4 equal to 0.125? No. So it's not a true equality. Okay? We're setting it up, we're testing it, we're trying to see if it is by subbing in those numbers, but that's technically not an equality. Okay? That means we can't make this an equals, and that this whole side of the expression that I'm solving for is not solving for Q, for K, it's solving for the ratio of my products to reactants as if it were K. And that solve happens to be a division. And if we do division, check me on my English language, a quotient is in reference to that division process. Okay? It's referencing the ratio of our products to reactants. Okay? So what do we call that? We'll call it Q. It's our pretend K until we know we're at K. That's Q. And so what we're going through and doing is to answer this question is what is going to happen to the reaction to get to equilibrium? Well, I have to make that 0.125 become 217, which means my number must get significantly larger. Well, how did I calculate the 0.125? I took the product concentration divided by my reactant concentration. So to make 0.125 into 217, what do I have to do? I have to make my product concentration larger. Okay? I need to make it a big number. How does it get bigger, though? How do I get more products? Okay? We can just go through and say, here's my box of stuff, and I just put in more products into it. Okay? That's fair. We could do something like that, but if this is a closed system, and I can't put in more products, where are the more products coming from? Where do I get products from in a chemical reaction? From the reactants. So by solving out this Q, I know what needs to happen. The product concentration goes up. I can't throw more products in there. But the reaction itself is going to change the balance of products and reactants so that it achieves the equilibrium. Okay? That was the whole point of, in fact, the graph that I didn't like, right? Okay, our reactant concentration goes down, our product concentration goes up. Okay, until what happens? We achieve equilibrium. And in that black section, I'm now at K. What this question is now saying is I'm over here somewhere. What I'm trying to decide is, am I at the point where I'm allowed to say I'm at equilibrium? Or am I before it? Okay? So what we're looking at is a random system and deciding, is this going to continue to change or is it done changing? Kind of make sense? So for this system, the N2O4 had to go up. The only way the N2O4 goes up is if the NO2, my reactants, go down. Make sense? Okay. What we can do is manipulate this a little bit. Sorry, not that button. And you can put it on a number line. Okay, and what this is referencing is our reaction extent, which is largely what our equilibrium is. Okay. K is products over reactants. Okay, at equilibrium. Q is equal to products over reactants everywhere else. Okay. And if we're going through and looking at our reaction, we can go through and say, well, the KEQ is 217. At 217, what does that mean? I have a lot more products than I have reactants. So we're looking at a number line, effectively, of 100% reactants versus 100% products. Okay? If we solve for the Q, we're on the reactant side of this. We have to shift to make more products to get to that K number. And that's the point of this number line. It's supposed to help visualize that process. Kind of, sort of? I mean, it's 10. Monday and Wednesday are more responsive than you guys. They're here at 8:30. Okay? Do it again. This time you solve it all out and you tell me what happens. Talk at your tables. So we set it up immediately. We should reflex into writing out what our K expression is, so we've got that. Okay. K is going to be solved the same way we'd solve Q. I did a color shift here at the end, trying to emphasize the difference between K and Q. Okay. If we go through and plug in those numbers, in theory we come up with 600. Cool. Okay, so what does that mean? Are we at equilibrium? What was our equilibrium? 21. So we're not at equilibrium. Okay, if we were to look at, again, that cruddy graph, I'm going to call it cruddy because I don't like it. Okay, and we look at our reactants and products, what does it mean if we have a Q that's at 600 versus 21? We have more products. So my product concentration, I'll put my red dot real high. Okay, and my reactant concentration will be lower. This is not to scale. Do not quote anything about scale. Come on, pen. Stop it. Freaking work. There it is. Blue dot. Okay, our blue concentration is lower. Okay, are we at equilibrium? No. Okay, what has to happen? We need more reactants. Our K needs to get to a smaller value, which means my reactant concentrations are going to go up at some rate, and my product concentrations are going to go down at some rate until we've achieved our K. This is a little weird, right? Typically, when we talk about our chemical reactions, what happens to our reactant concentrations? They decrease. Why? Because we're trying to make a product. Okay, we're looking at the forward reaction. Why would we ever see a system where we had more products than reactants? If the system was knocked out of equilibrium. Okay? Most of life hovers around equilibrium, but if nothing changed, what happens to us? It's a somewhat decent response. Nothing. The only reason we move is because our bodies somehow knocked the system out of equilibrium so that that motion could come into place. You're looking at passing ions across a channel. Okay? So our bodies hover around equilibrium, but we're constantly pushing out of equilibrium to cause an action to happen, to breathe. to have our heartbeats, to move our hands, to think. All of those are non-equilibrium systems. So why would we ever look at this? Well, most of what we deal with or what we find interesting is how do our bodies knock out of equilibrium and how do they return back to equilibrium? If we understand both those directions, we understand a whole lot more about the fundamental system of how things get put together. Does that make sense? So realize now what we're shifting out of is, it always goes forward, to recognizing the power of that backward reaction and how things can constantly be changing on us. Okay? If we push it to a number line, we can again see our number line and see where we're at. Our Q places us at too much products. To get to the K, I have to slide towards the reactant side, which means my reactant concentration must go up. But the reactant concentration goes up by doing what? Reducing the products. Make sense? Hi. What this introduces, again, is the reaction quotient. The reaction quotient is calculated the exact same way that we calculate our equilibrium constant. Okay, it's the same general principles. Okay, what we would then push to is what is the relative value of Q versus K. Okay, those relative values are now going to dictate what our reaction is going to do to re-achieve our equilibrium, because all of our reactions are going to strive to get to equilibrium. Okay? If this is something that you don't think you can memorize or maintain, what should you do? Write it on your cheat sheet. Okay? What would happen to the concentration of CO if the reaction is initially at equilibrium and we added more CO2? We've got the KEQ on this line. Okay, if we're saying this system, we were at equilibrium, so we could go through and say our K. CO, we have to square it because of the coefficient, H2 squared. Hopefully this fits in on the bottom of the screen. Our CO2, our CH4. Okay. Again, we're shifting across to our Q. Okay, we were at equilibrium, and now what did we do? We increased the reactants. So this CO2 value at the bottom became bigger. Attempting to make it for emphasis. Does everybody see that? Cool. Are we at equilibrium anymore? No. Okay. Where would our Q value be? It should be lower than our K because we've increased the concentration of our reactants. Right? Where specifically? I like that response. How would I know? Good point. We don't know. We didn't say how much more CO2 we added. We just added a bunch of CO2. Okay, so we just know it's somewhere lower. Okay, so our Q is lower. So now what's going to happen? Now that I've added this CO2, am I at equilibrium? No, so what's the reaction going to do? Go to equilibrium. How does it go to the equilibrium constant? What do I have to do? Say again? I have to increase the concentration of the products. How do I increase the concentration of the products? Decrease the concentration of the reactants. That's how my equilibrium or my system, my reaction, is going to reattain equilibrium. If I've got those expressions written down, I can track through all of those pieces. Okay. It's not obvious up there, but it is in the notes on the slide. So we should go through and talk about it a little bit. What we just addressed there was all which aspect? Is this kinetics or thermodynamics that we use to explain the increase in the concentration of our products? It's thermodynamics, because what did we look at? KEQ. And KEQ is strictly thermodynamics. Okay? How could we explain this kinetically? It's going to come back to potentially our activation energies or looking at our rate increases. Okay? So let's look at the rate increase. Which rate would you expect to increase? The forward reaction rate must increase. Because what are we trying to produce? More products. We've established how the system needs to shift. Now we're taking the kinetics to help us to explain what has to happen to the kinetics to get us more products. Does that make sense? Okay. This system that we effectively just walked through was an observation made by, I'm pretty sure, a French guy, based off of his name and the pronunciation, Le Chatelier, that might be pronounced right. I honestly don't know. Really just goes through and says that if a system is at equilibrium and is stressed, we'll talk about in a second, the system will experience a shift in response to that stress that reestablishes equilibrium. Okay, so we were at equilibrium, then we added, I already forgot what did we add. We added more CO2, is that what it was?
Yeah.
Okay, we added more CO2, oh yeah, that was a reactant. Okay, and what did the reaction do in response? It tried to get rid of that CO2 by making more product to create a balance. Okay, the way that, or there's a couple ways that I like to think about Le Chatelier's principle. Okay, one, if you just see a friend standing on one foot and trying to balance, what are you going to do to that friend? And some people laugh because you clearly know what you're going to do to them. You're going to push them. Okay? If it's some random stranger, you probably weren't going to push them, so it has to be a friend. Okay? And you're probably not, well, you could be, but you're probably not that friend that goes up and shoves them to the ground. You're probably just going to give them a light tap to see what happens. And if you give them a light tap, they're going to move that direction, and then what do they have to do? They're going to have to wobble back, and you'll get this back and forth, this oscillation, until they obtain equilibrium again, and they're now rebalanced. So when we're talking about our chemical reactions, it's our friend sitting there balancing, and now what we do is we mess with them a little bit. Okay? We give them a little push and say, what do they do? How do they respond to that action? At least initially. Post, they might punch you, okay, depending on what they were trying to do. Okay, kind of makes sense? There's a couple kind of analogies that come along that can kind of explain these. You could look at a seesaw where you've got reactants and products. It's perfectly balanced, right? If I come through and add a stress by putting more products on it, it's now out of balance. Okay? The chemical reaction tries to correct that imbalance by doing what? Taking a chunk of those materials and giving them over to the reactant side until what has happened? We've re-achieved equilibrium. One of the problems with this analogy is then students go through and say, oh, so the reactant concentrations must always be equal to the product concentrations. Well, was that true? No, in fact, almost none of our examples showed that. So how could this possibly work? The fulcrum is our K. Okay? That fulcrum, that center point, can be anywhere along that seesaw, which is going to change your concentrations of reactants versus products. Okay? So it doesn't mean we're always static at a 0 point. Okay? It just means we can slide that value around our fulcrum to change the balance of reactants and products. Kind of make sense? Okay. The other problem with this, as an example, is that once it is balanced, how much do the reactants and products change? They don't. We would just see the boxes of reactants, the boxes of products, and we would say the reaction stops. But that's not true, right? We're dynamic equilibrium. It's constantly changing. Okay? So a better representation would be if the reactants were constantly shuttling things over to the products and the products were constantly shuttling things over to the reactants. But if you think about a seesaw and you put two kids on it and you started chopping up the kids to pass them across the seesaw, that gets a bit gruesome and we don't like that analogy anymore. Okay? But that's effectively what's happening with our equilibrium. So a different example, I can take two containers and I'll separate them with a little trap door at the bottom. Reactant and product. I fill up the reactant one. Now I remove the trap door. What happens? Whoops, volume appears. That was like perfectly spaced. That was interesting. What happens? This shifts over to the product side. Until when? Does it all shift across? No. It shifts across until, again, with the words. It shifts across until we've achieved equilibrium. I could again pretend and put the trapdoor in. What happens if I put a bunch of product in there now? Okay. Remove the trapdoor, allow it to rebalance out, and now what happens? Product level drops, reactant level rises until we've achieved a new equilibrium. Once we've achieved that new equilibrium, does the liquid stop moving from each of those chambers? No, you're still getting motion back and forth between those. This one, again, people go, oh, it's the same concentrations, reactants and products. Stupid letters. I could change the size of the individual chamber, where my center wall was located. The location of that center wall is effectively my equilibrium. So I'm, again, looking at the potential for reactants and products being different. This one's a little bit better because it represents constant movement or allows for constant movement back and forth. Kind of make sense? Okay. So those are secondary representations for your equilibrium. Okay. So what are the types of stresses that we could do? Okay, well, before we get fancy into that, because you didn't read anything, right? You didn't read it, right? Good. What was K? Products over reactants. Good, do better. Cool. Our brackets meant concentration. What are the units on concentration? Moles over liter. Moles over liter, right? If I change the number of moles, is that going to change my concentration? Yes. Okay. What if I change my volume? Yeah, that will change my concentration because volume is liters. It's part of concentration. What if I change the pressure? And now we got to stew on that one. What do you mean pressure? Pressure can't be represented as a concentration, right? PV equals nRT, remember? Pressure equals N over V times RT. What was N? What are the units on V? Liters. What is pressure representative of? Molarity. There it is. Okay. So changing the pressure, changing the moles, changing the volume will all have effects on concentration. How they affect concentration, now you have to nuance and say what value are you changing, where is that manifesting? Kind of make sense? Okay. To that end, you could go through and deal with all the systems, or because you have a cheat sheet, you could go through and identify. If I increase the volume, it does this. If I decrease the volume, it does this. If I increase the pressure, it does this. Make sense? So you could identify all of those pieces. So if we're looking at the types of stresses, changing the concentration, changing the pressure or volume. Changing the pressure or volume works because pressure and volume directly tie back to concentration. Okay? So this is bulleted out as two different things, but really it's just one thing. It's just recognizing the power of the units. Quiz 1, when you lost all points for not showing your unit work, ta-da! It shows the power of including our units and understanding what they mean and how those manifest into our systems. Okay? I can totally understand seeing this as two bullets. Okay? Not necessarily because of the things you're changing, but of the substance that is allowing that change. So bullet number 1, you're changing things for your aqueous systems. Bullet number 2, you're changing things for your gaseous systems. Kind of makes sense? Okay. Okay. And if I change the products or reactants, does my equilibrium constant change? If I change the concentrations of my products and reactants, does my equilibrium constant change? No, it does not. The equilibrium constant is constant. It doesn't change. But if I change the concentration of my products and reactants, what am I changing? I'm changing Q. What I'm doing is shifting away from the equilibrium. Now the reaction, with a mind of its own, has to figure out how to re-achieve that K balance, that equilibrium constant. Well, that was not the button I meant to push. Hi. So, new question. Predict what would happen to the concentrations of CO2, CH4, or and CH4 if the reaction was initially at equilibrium and H2 was removed. Write out your equilibrium constant expression and use it to help explain what happens. Okay, it's a blue box. Talk to the people at your table. Try and piece it together. What's the first thing you should write down? What is your equilibrium expression? Get that written down. That needs to be your reflex anytime you solve these questions. Get that expression in front of you so you can start to manipulate it. Look at this one. I actually need to go backwards real quickly because I had a quick question that I meant to ask. So if we go backwards and look at your notes for this one. What things were in your KQ expression? Concentration of what? What were the products? It's not a trick question. What were the products? CO2 and H2. What were your reactants? CO and H2O. Do we include H2O in an equilibrium expression? There's an important statement. Okay? H2O, depending on how you remembered us talking about our equilibrium expressions, you might be like, oh, I don't want to show that. You only remove it if and only if the phase is a liquid. This phase is not a liquid, it's a gas. Okay? So things disappear from your equilibrium expression if they're solids or liquids because their concentrations stay constant. Okay? If they're gases, you leave them in. Which, here, right? Yeah, so if we wrote this out, so I harped on a couple people because they wrote the KEQ, H2, CO squared, CO2, CH4. And then they said, what did they say? Products increased. Cool. If you're being asked to explain, did you explain anything? if I said this was an explanation, are you satisfied that that's an explanation? No. So don't write that and expect me to be like, oh yeah, it's perfectly acceptable. You aren't going to accept it from me. Don't accept it from yourself. Okay? So yes, that's the KEQ. You are trying to say what's happened. Okay? But why did it happen? Okay? This is where I would argue I would draw a Q, okay, and I would get all pictorial with it, because the reaction says, or the statement says, H2 was removed. If H2 is removed, my concentration of H2 is really, 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 really tiny, right? CO2. Which means my Q value is going to be small. Okay, and in fact, a better description isn't just small, it's smaller than my K. Okay, smaller than K. And if I have a Q value that's smaller than K, what needs to happen? Now I need to make products, so my product concentrations should increase. Kind of get it? So it's not just this and this. You have to be able to tie those concepts together. Okay? And even with the explanation that's up here, a lot is kind of lacking because we want to kind of explain what's going on within that smaller K to shift from Q to K, products must increase, right? We're now using some of the English language to help us actually describe and explain what's happening within this. Does that make sense? Yes, and it is.
How can CO2 react with H2 for the reverse reaction? H2 is not in there. If you take away H2, how can it react with CO2?
Am I doing the reverse reaction?
How can it be like an equilibrium?
So, let's see if I can pull it off. We have a K, so this is reactants, this is products. Our K is 417, which means we have lots and lots of products, which means my fulcrum is going to be over here. Okay, there's my reactants. Does that kind of make sense so far? If we go with our fulcrum system. Okay. What have I done? I've gone through and I took a chunk of products out. Would I be balanced anymore? No. Okay, so what has to happen? What would happen if I took that chunk out is I'm now twisted this way. Make sense? So to reattain equilibrium, what must happen? I have to take a chunk of my reactants to backfill that spot. Okay? So in that scenario, what am I changing the concentration of? What is the reaction changing the concentration of? It's modifying the reactants, not the products which your initial statement surmised. Does that make sense? Okay. I want to push on that a little bit too. Does it say how much H2 was removed? No. So even if I removed H2, could I still get the reverse reaction? Yeah, I don't know how much. Okay. If I took all of H2 out, can I get the reverse reaction? No, because it's not there. Will I eventually? Yes, because the reactant will convert to product. Now I've got some product concentration. Now I could do a reverse reaction. So remember the equilibrium, both reactions are going to be happening, but if I remove all the product or all the reactant, I can only get one direction of the reaction to happen.
So it doesn't really matter like how much was removed, it could be all of it, it could be just
Yes. We would need to be a little bit more clear within that statement on what's going on within it. Does that make sense? First you and then me.
Why didn't you put the Q part on the other side of the one?
Because I don't know the magnitude of the number.
Okay.
Is all that is.
What's most important here is that you're just showing that Q is less than
Yes.
K.
Okay. So if you wanted to show that Q with that blue dot all the way the hell down here, go for it. Not a big deal. Okay. We didn't quantify it If we had said H2 was entirely removed, that's still
Nice.
product. That's still the product side. We should shift away onto the other side of that 1 if we lost all of the H2, because I'm missing a product now. Okay. The biggest deal here is just to know where it is relative.
I think you just answered my question.
Oh, you're gonna do the same
I was
thing?
gonna ask if this would even occurred, is how did you take away a product that wouldn't balance the equation anymore?
So that's an interesting question too. What we're looking at is effectively a flask that has all of these things within them. Okay? And what we're doing is we're looking into that flask and selectively pulling out certain particles. Okay? Is the reaction chemically balanced? No. Okay? Because I'm missing some of that H2. So my chemical reaction technically isn't valid anymore because I don't have that species. But if you go back and look at any of your chemical reactions that you talked about in 151, you balance them out, right? You balance them out assuming what happened. The reaction continued forwards. So all we're doing is removing it from the reaction, the species. We aren't changing the equation. The equation is still constant. Does that help?
Okay, so H2 goes down, which means Q is less than the K. I understand that part.
Yeah.
But like everything's pointing to the products increase, which is the exact opposite of what we're saying.
And so this is where we got to be a little bit careful. The product concentrations increase. I've removed H2. What's my concentration of H2 at that point? Let's say we remove it all, so we can actually give a numerical value. What is the concentration of H2 at that point? 0. Now what's the reaction do in response? Creates more products, which means it's no longer 0. What happened? The H2 concentration goes up.
What's stopping the reactants, the bottom, to make less? Or no, okay, that's what we're talking about, where it's like a closed system or whatever. Okay.
Yep.
Okay,
Yeah. Because it's achieved the balance. It's already there. Stuff is moving back and forth. And the best way to kind of think about it is the water example. We lock it off. We say that we can't transfer any more liquid back and forth. I now come in and I drink some on one side. It's now removed. Okay? It's now permanently removed, which means my total particle count when I go back to equilibrium is going to be lower because I've removed some of that particle system. Does that make sense?
Yeah.
Okay. So total particles, everything is going to go down total, but what's going to happen to my products? My products are going to have to go up because they're currently lower in level than my reactants to reobtain that equilibrium. Are they going to achieve as high as they were before? No, they can't, because I have less particles present.
Okay, that makes sense.
Right? We good? Let's see. Do I get lucky? Ooh, no, I don't think I got lucky. That seemed like a lot of buttons. Nope, I was right. Right? Or is that's a new one? It's a new one, isn't it? Yeah. Right? Predict what would happen to the concentrations of NO2 and N2O4 if the reaction was initially at equilibrium and we decreased the volume. Okay? Think about what happens to the concentrations and the reaction rates. Okay? This one's spinning a little bit different because we're talking about now our reaction rates. What we think? What do you think is going to happen? If we decrease the volume,
Forward reaction increases.
okay, forward reaction increases. Why?
So decreasing volume increases molarity across the board.
Okay, so let's pause right there. Okay. First thing we've got to do is get it out of this unit of volume systems because that's not what we are using or what we're used to working with when we're talking about our K expression. Our K expression is in units of concentration. So let's get away from the volume system and into a concentration system. Okay? Now what? So if we decrease the volume, what's going to happen to our concentrations?
Concentrations go down, or they go up, sorry. They go
Right.
up across the board.
Right, and I will pause on that too, because again, it goes up or down, right? That's a 50-50 flip. So best approach to that is if you don't remember your concentrations, so molarity equals moles per, and I heard someone say what I wanted you to say, moles per volume, okay, which is liters, but if we put it at volume now, that can help us back to this. So if the volume number gets smaller, what happens to my molarity?
Increase it.
It gets bigger. So writing that expression down can help minimize some of those secondary mistakes. Okay, continue. Our concentration goes up.
And so if concentration goes up across the board at a relatively equal amount, the squared value is going to increase more,
Okay.
which is the reactance.
If we're changing that volume, all of our concentrations at raw form are going to go up about the same. But if we're looking at this K expression, I'm squaring that concentration at the bottom. Okay? Which means what's going to happen to the denominator? It's going to increase. And if the denominator gets bigger, I'm now looking at a Q
Lower than
That's a little sloppy there. Little is an understatement. Okay, I'm looking at a Q that now is significantly smaller. So what has to happen?
reaction.
I need to run the forward reaction. Okay, that expression or that talk through meant what? What did we look at? Kinetics or thermodynamics? That was only thermo. Okay? We didn't talk about the speed of the reaction at all. Okay? So it's going to come down to where's your comfort level with this explanation. Okay? If we can see those concentrations, we can use thermodynamics to explain it, and then what can we do? Backfeed the kinetics. Okay? How do we backfeed the kinetics?
Rate of forward reaction.
The rate of the forward reaction must increase so that I can obtain that KEQ.
How does increasing the molarity of the whole reaction by decreasing volume mean like a smaller Q and presumably less product?
Okay, so if I decrease the volume, my concentration increases. Okay, let's try it this way with some numerical systems. Okay, let's say we start with, we'll see how this works. We start with 1 molar for each of these concentrations, right? So 1 over 1 squared will get us 1. Let's call that our KEQ. Leave it at that. We're just spitballing. We're saying that's KEQ. Okay? Now what I want to do is decrease the volume. Okay? If I decrease the volume, what happens to my concentration? It goes up. I'm spitballing numbers. So I want to decrease the volume twofold. What's going to happen to my concentration? It doubles. So instead of it being 1, it's going to become 2. Which means the other one is
Also 2.
also 2.
Squared.
Go through and calculate. This is now 1/2. Okay? The reason the KEQ is changing is the Blumen exponent. Okay? That's the part that you're missing. You're saying, well, if the concentration drops, everything drops fairly, shouldn't it be at KEQ? No, because KEQ has a twofold factor that I have to account for in that expression. That's why we're seeing that shift across.
But if it was a equilibrium reaction where both were first order, then it would be a KEQ.
Yes. Yes. So it's really important to know our KEQ expression with those individual coefficients. Oop, Oh, I just deleted everything.
Do we know that products and reactants are one to one?
No, okay, and I knew I was going to get in trouble for that. So what I went through and did is ultimately deleting all of that, and I just said, for giggles, let's say at equilibrium, our concentrations were 1-to-1. We're saying that our equilibrium constant is 1. Okay? So that when I go through and solve, I've got numbers that allow me to manipulate this. Okay? A more appropriate response, that there's no way I'd be able to pull it off in my head well, okay, would be subbing in the appropriate concentrations to get me a KEQ of 217.4. I could probably pull it off. There's no way I'm doing that on the fly. Okay? So what we just went through and did is just said, well, just for giggles, let's call it 1-to-1. What happens if I change the change the volume? Well, my concentrations are going to change. How do my concentrations change? How does that manifest into my K expression? And because we have that exponent, we can now see that visually with the numerics that may not have, I would argue, was not obvious without the numerics. Does that make sense?
When it asks about reaction rates, does that get into the kinetics?
The reaction rates is now the kinetics. So what we went through and did was processed what had to happen. Okay? We had to form more products. And if we have to form more products, what does that mean about the forward reaction rate? It has to be going faster because I have to produce more products. Okay? You could also say the reverse, the reverse reaction is happening slower. Okay? But ultimately, it's happening faster to account for the more particles of our NO2, that higher concentration. Okay? Kind of makes sense? That's dealing with it numerically through K. I'll say there's another way to do it that just happened to dawn on me that I remembered when I was taking this ages ago. If we're decreasing the volume, which side of the equation is going to feel more pinched? The one with twice as many particles or the one with one particle? The one with twice as many. So the stressor is I decrease the volume and now the one with more particles is like, there's no space. What do I need to do? I need to react to become less pinched. Make sense? So you can manipulate based off of the number of particles as well. That's now avoiding dealing with that K expression and that exponent, but you kind of have to think about this kind of pinching aspect.
If this like the sign is different, if one was a liquid, one was a gas, would that change things?
Oh yeah. If one was a liquid and one's a gas, now what's going to happen?
We need to take that into account.
Yeah. So if that was a liquid, okay, and I change the volume, is the volume change really going to have any effect on the liquid? No, the liquid's not going to care. What's going to care? The gas. So if I decrease the volume, the gas is now frequently bumping into each other. We increase the rate of collisions, faster rate, I form liquid. Make sense? Okay. Volume, pressure, equilibrium. Okay. We've actually done this now a couple times. Pulling back to PV equals nRT from Gen Chem. Okay. You're looking at how all of those systems are interconnected and related to each other. In all of those cases, our KEQ does not change. The numerical value stays constant with those changes. Okay? But what's going to end up happening is our Q will now change. We've created a stressor to the system that's going to cause it to shift away from that stress. Kind of, sort of? Okay. How does adding a catalyst affect the rate of the reaction? So I've got a reaction here. Ta-da, reaction. If I was to add a catalyst, how would my picture change? Okay. So referencing the activation energy, so we could show we have an activation energy here, and if we add a catalyst, our activation energy needs to get smaller. was supposed to be a nice straight line. Okay? What do I look at? How does it affect the rate for the reaction? Rate goes up. Okay? The rate goes up because I have a smaller activation barrier, it goes faster. Cool. How does it affect the equilibrium constant? What rate goes up? The reactant to product rate goes up, right? Because we have a smaller activation barrier. And if that rate goes up, what does that mean happens to Kf, our forward rate constant? It gets bigger, which means what should happen to K? It gets bigger. Did you talk about Kb yet? What happens to Kb? It's on the energy diagram. Kb initially is dependent on that activation energy. When we catalyze it, it gets smaller, which means both Kf and Kb or Kr, depending on how you want to look at it, get smaller. And if they both get smaller, what happens to K?
Is it proportional?
It is proportional. Okay? So adding a catalyst does not change the balance of our equilibrium. We still have the potential to go to reactants and products. So our K expression stays constant. But adding a catalyst does give us an extra benefit. The extra benefit of a catalyst is that when do I achieve equilibrium? I achieve it at the same place, but when? And this becomes weird to, I can't talk about time with equilibrium. We can talk about when we got to equilibrium. It's going to get there faster. That's the point of the catalyst. It helps us achieve that or get to that balance point quicker, which is good. We like that. Right? That means we can get out of lab faster. I'm drawing. Okay. So our conditions that affect equilibrium: concentration, volume and pressure, temperature. How does temperature affect our equilibrium? It's on the screen. How does temperature affect our equilibrium? You're bringing in thermodynamics from a thermodynamics class. Don't do it yet. Temperature is going to affect your equilibrium constant. Why would it affect your equilibrium constant? Okay, bear with me here. Actually, here, I'm going to try and do this gracefully instead of making everybody seasick. Instead, I'll just make myself seasick. What does temperature affect? If we increase the temperature, what happens? Our K is affected. And interestingly, if we have an endothermic reaction, our K increases. If we have an exothermic reaction, our K decreases. A goes to B, right? Chemical reaction. If it's exothermic, where would I write a heat term? If I increase the heat, we're putting a stressor on the system. It wants to navigate away from that stressor. By doing what? by increasing the reverse reaction rate. And if my reverse reaction rate gets larger, what happens to my K? It gets smaller. Ooh. Remember when we did our enthalpies at the beginning, and I said I like incorporating the heat term into my expressions because it helps me understand. Ta-da! So if you were struggling on dealing with what happens with our K, with heat, if you incorporate the heat into the expression, it can help you see how our system is going to adjust to calibrate against it. That's kind of neat. And we're now here. So our temperature has a direct effect on our K. And we could do that the way that I manipulated, or you could do that by going back to that lovely quadrant system. How important is that quadrant system? That's really important. Do you think you'll see some questions based off of that quadrant system? Yeah. Okay. So if I looked at everybody's cheat sheet, what is everybody's cheat sheet going to have on it? That stupid quadrant system, so that you can manipulate and use it to work your way through answers. Okay? So when you go through and look for quiz 2, you need to be able to predict and explain the changes that occur in a chemical reaction. If we change those things, what's going to happen in our chemical reaction? Okay? So predict what would happen to the concentrations of CO2 and CH4 at equilibrium if H2 was removed. Write the equilibrium constant expression and use it to help explain what happens. Which looks exciting. This looks like lots of stuff. So didn't we do this one for now the sake of the recording? We removed the H, but now we have delta H and delta S. Do you need delta H and delta S? No, because we answered it without those. So we've answered it already. Okay, we don't need to bring in the delta H and delta S. We could go through and use those to calculate a delta G. Once we have a delta G, we could use the delta G to calculate a KEQ, okay, which would be great. We could go through and quantify all this stuff. But the question isn't asking that, so I'm not quite sure what's going on with that. Okay, this is an important question that I would highly recommend you review. All together. Okay, and I would argue this is the end of content. If we look at the remaining slides, just because we're close and everybody's getting excited. Oh, well, that clock is slow. The remaining slides are now going through and saying, what can we do for this particular reaction? And talking about all the systems that we could play with. Okay, all the things we could manifest and play around with. We could also go through and look at what's happening at a chemical level with that salt dissolving in water. We already technically talked about this one, but I believe these slides are now getting, oh God, that just gave me heartburn. Quantifying the bejesus out of it so you could see all those individual numbers and see like, oh yeah, like, cool, we can approximate that without having to quantify it, okay? So the rest of those slides are really just practice, okay? So next, all right, now I'm going too far. Nope. Next week, what are we, Thursday? We're Thursday. Tuesday, we'll talk through this question, going through all the approach. You'll also notice that there were a couple simulation things that popped up. In the interest of time, I wanted to make sure that we got through the content, so I didn't pull out those simulations. So on Tuesday, we may play around with those. We may work through the examples. We'll definitely do this question as a class, and then we'll kind of open it up to see what questions you guys have in preparation for Thursday. Make sense? The quiz 2 is Thursday. Okay? And then we get spring break. At least you do.